Last time, what did we talk about? Yep, we talked about rate. We talked about overall rate and how to define that, right? And that was through calculus terms. However, we could get like a number, but is that number really useful when we're talking about kinetics? Like, it's helpful, but what do we really want out of kinetics? What was that? Yeah, how fast will it happen under what conditions? What'd you say, Lily? Sorry, I didn't hear what you said. That is helpful. That's one set of conditions, though, right? What would we like to know? Yeah, any conditions we want. What are we going to use to get that? Or in your lab, what were you trying to figure out with that crystal violet? Yeah. Reaction order. What we want to know is we want to know the rate law. Not the rat law. And we said we wanted to ditch the new for rate. We just want to write rate, right? Okay. How does a generic rate law look? Got rate is proportional to, we're not going to change it to an equal sign yet. We'll get there in a second. What do we need on the other side? We will need a rate constant eventually when we get to an equal sign. We're going to leave the equal sign off now. What's rate proportional to? Mm-hmm. Yeah. It isn't always the stoichiometric coefficients. We'll talk about that in a little bit. It is for an elementary step. A, and let's say B. What are A and B? Yeah, these guys are reactants. And these things, A and B, or little lowercase a and b, what are they? Yep. Reaction orders. Okay, Tessa, you wanted to toss an equilibrium or a constant in here. What would you do to make this be an equal sign? Yeah. This thingy, right? Okay, that's really what we want. You guys want a refresher on what these order things are, or do you remember what they are? Refresher? Okay. Reaction orders. Oops. Okay, so let's say we have the following generic rate law. Like that. We can consider the orders of each individual species or the overall order. What's the overall order? You remember? Or how do you figure that out? What was that? Yeah, you just add them together. 1/2 plus 2, total of how much? Yeah. That's not the only way we could describe this, though. If I write WRT, do people know what I mean by that with respect to? What's the order with respect to A? Yep. What about order with respect to B? Yep. Feel like you remember that bit about it. Okay. Now, what do these things mean? They give you an idea, if you were looking at a mechanism, how to break these things down. Can you ever prove a mechanism is true? Like 100% that a mechanism is true? No. What can you prove with absolute certainty, though? What was that? Yep, you can determine order. And then when we're talking about mechanisms, let's say we can't ever prove it's 100% true, but what can we definitely do? That's a tough one. We're going to leave stepwise and concerted alone for now. Yeah. Yes, you can definitely prove that this is not happening. Why can we do that? Well, we can't isolate a transition state right now. We're getting really close with like femtosecond lasers where we can probe that time on which chemical reactions actually occur. If we ever get to picosecond lasers, yeah, it's femto. Which one's smaller, pico or femto? Okay, yeah, so femto is smaller than pico. So we'll get there. Okay, we care about getting this thing. But how do we get the rate law? So how do we determine that fridge is really long today. Now all you're going to be thinking about is the fridge. I shouldn't have said it. What's that? I don't know. I actually think it's the block on top. Or maybe all the crap I've piled on it. There used to be hops in here. There is Dr. B's weird mixture. She does like half diet, half regular. I don't know how anyone. Like, you want diabetes and cancer? Let's go for both. Like, I don't know. Yeah. So back to this thing. How do you figure that out? Like, how do you figure out a rate law? So I guess I'm asking it even more basic than that. You're correct. That's the method of initial rates, which we'll get to in a minute. But how do we have to determine a rate law? Like Lily said something about coefficients, like looking at a reaction. Can we do that? How do we have to figure out a rate law? Can you be more explicit than knowing them? So if we have only the balanced chemical equation, can we determine the rate law? No. What do we need? Yes, we have to measure the concentrations and we have to do an experiment. Can hypothesize, but you have to do an experiment to figure out the rate laws. They're determined empirically. Have you guys used the term empirical before? So they come from experiment. There are a handful of different methods, including that like femtosecond laser thing that I was talking about. Tessa, you actually talked about one called cell flow, a cell flow method where you like pump stuff in for your talk. Who else had kinetic stuff in there? Ellen, I don't remember. Do you remember what they did? Were they keeping track of it through UV vis spectroscopy? Yeah. HPLC. Okay. Yeah. So they still were probably using. Were they getting masses or were they? Yes. So that's also another method. The method, the two that we're going to discuss are probably the most common ones that you will see. There's the isolation method. And then give yourself a little bit of space if you have it on your paper, like maybe a quarter of a page. And then we have the method of initial rates. Ellen, you described something a little bit ago. What was your experimental setup? Yes. So here you change the constant, or I'm sorry, you change the concentration of one reactant, but hold all others constant. Now, where does the term initial rates come from? What's that? Actually, what you did in experiment E was this guy, and we'll talk about that one in a minute. Initial rate. What do we mean there? Yeah. Not even to that point. You look at it in a window right at the beginning. You do not consider it going out to equilibrium, because what do you have to do with equilibrium? Like, if you want to study equilibrium, you set up an experiment. How much time should you give it? A lot, if you want to study equilibrium. Here, it's right off the bat. So you measure rates at the start reaction. What is the downside to that? What the hell? Have any of you guys ever watched the show Balls of Steel? Okay. When you're bored, look it up on YouTube. What it was a bunch of people in Britain playing pranks. And what they would do would be like, I don't know, there was one that was a devil. This guy dressed up like a devil and just annoyed the piss out of people. It was the funniest thing ever. But at one point, has anyone ever seen a smart car before? Okay, how would you describe a smart car? Yeah, the tiny one. It's like a go-kart. So what this little devil guy would do, I should have drawn him in red. We'll get him in red. There we go. Sitting there, he had a cape and a pitchfork. That's a shitty pitchfork. All right. And what he would do is if anyone ever been to the UK or like out in the countryside portion, what do you know about their roads? They existed before like traveling roads existed. So they're extremely narrow. You can't pass anybody on these roads. If you're stuck behind slow traffic, sucks to be you. So what he would do is he would wait until there was a big tractor. Here's my tractor. And he would slow down in front of that tractor. And then there would be a ton of other cars behind him. Now, the way that the camera would work in these shows is it would pan that way. So let's say our camera is us studying a reaction. Method of initial rates. Boom, done. What's the downside to method of initial rates? You don't get the full picture. So that's a con to method of initial rates. You are only looking at the start. That may not be how the chemical reaction actually proceeds. Reaction order might change when considering a longer timeline. Again, the show was called Balls of Steel. Look it up. It's really funny. There was also another guy who would do urban sports. And one of the urban sports was urban bull riding. And what he would do is find the biggest person he could see and jump on their back and hold on as long as he could. Very entertaining. The pros to this one, though, are you can get the order with respect to any reactant you're considering. The isolated method, that's exactly what you guys did for your experiment. How was your experiment set up? You measured the decay of crystal violet. Was that the only thing involved in the reaction, though? What else was involved in the reaction? Yeah, the hydroxide. What did you do to the hydroxide ion concentration? You did vary it in different solutions, but what can you say? Did the concentration really change? No. So what you do here is the concentration, all reactants is large except for one. That one's really small. And there's a problem with that. What's the problem with that? Do one at a time. These concentrations are really large. That might not be the conditions that you're interested in. At lower concentrations, the mechanism changes. Did you guys ever tell you about the time I wasted an entire semester synthesizing something? Okay. Am I okay to erase this? For 2 years of my life, I worked on synthesizing these types of compounds. These guys are known as polychlorinated diphenyl ethers. They're flame retardants. They're in the Great Lakes in relatively large quantities. And if you look in the Indian Oceans, around India and China, they're polluted heavily. You look in their watersheds, heavily polluted here. I had to synthesize these so I could make a standard because there weren't standards at the time for them. So I could make these things, then I could identify them in the Great Lakes fish. Don't eat walleye from Lake Erie. Full of these things. Okay? I love the walleye from Erie. My advisor, I asked him, how bad is it? Like, and he said, young guy like you, probably 1 or 2 a month. Like, what if I was a pregnant woman? He said, I would not eat anything out of the Great Lakes. Like, what about you? I'm an old guy. I'd eat 1 every week. Wouldn't bug me. I'm on borrowed time as it is. Now, I got to a step where I had to add fumine nitric and fumine sulfuric acid. Does anybody know what those things are? They're extremely dangerous. They are so concentrated with gas. So like when you make an acid, you flood gas through and it sucks it up. So HCl, you're flooding in hydrogen chloride. It's just sucking up as much hydrogen chloride as it can. This, you open the cap and gas starts spitting off of it because you've pushed more gas than needs to be in there. They're really strong acids. During the synthesis of this stuff, I had to add it dropwise. That's what the procedure said. I had to translate the synthesis from something in German to English, which was a task in itself. And it said, add it dropwise. Why the hell would I need to do that? Who cares? Boom, I dump it all in at once. Never got any of my product. I did that for 2 years. I literally tried to optimize this reaction as much as I could. I'd spend about 15 hours a week synthesizing this stuff, and I just couldn't get it to work. And the one day I went, you know what, fuck it. I'm going to add it dropwise. I added a drop, and bam, solids started to form. I made it. I couldn't believe it. Do you guys know what I did that was wrong? Like, why does adding it dropwise matter? The kinetics change based upon the concentration of what's in there. So the other method we're talking about, the isolated method, may not accurately get the kinetics.